I'm sharing the screen. Yeah, is my voice is clear now? Just give response so that I will move forward. Anyone? Is my voice is clear now, ma'am? Hello. Is my voice is clear? Anyone? Okay.
Yes, sir.
Okay. Thank you. Okay. So today we discuss about this job opportunities in VLSI semiconductor industry. Okay. I think my screen is also visible. Okay. So basically these are the agenda. So VLSI semiconductor industry introduction, physical design, physical verification, analog layout, AMS and custom IC layout, ASIC or chip design flow. Okay, about Gnanodaya. Okay, our placements. Okay, so these all we discuss. Okay, so basically like realize a semiconductor industry. So basically there are like three types of industries in the VLSI. Okay, so one is product based company, service based companies and EDA companies. Okay, so product based companies are nothing but the companies which will produce their products. Okay, like you have Intel. Okay, Intel, AMD. Okay, AMD, Qualcomm. Okay, these are nothing but product based companies. Okay, and service based companies means this will not produce any product, this will give service to this product based companies. Okay, so these are nothing but service based companies, and EDA companies are nothing but electronic design automation. EDA is nothing but electronic design automation. So basically this will provide some tools. Okay, some tools for both front end as well as back end. So like Cadence, Metagraphics, okay, Synopsys, these are some EDA companies. Okay, so these EDA companies, products and service based companies, okay, will always be synchronous. Okay, they will combinedly work together to meet the technology deliverables. Okay, with support of VLSI engineers. Okay, with the support of this VLSI engineers, these will combinedly they will do combinedly they will work together. Okay, so here you see, so these are the top 20 product based companies like so product based companies: Samsung, Intel, TSMC, okay, and Micron, okay, Qualcomm, Nvidia, Broadcom, MediaTek, TI, okay, AMD, Infineon, Apple, ST Microelectronics, okay, NXP, Analog Devices. Okay, these all are nothing but top 20 product based companies. Okay, so they will produce their own ICs, or like they will produce the chips. Okay, so these are product based companies. And next service based companies, these all are service based companies like Capgemini. Okay, and some companies like L&T, HCL, Wipro. So Wipro have the VLSI division. Okay, and like E-Infochip, Samsung. Okay, so Mirafra. Okay, some companies. Okay, so other than this, apart from this, there are some thousand plus service based companies are present in Hyderabad, Bangalore, as well as Noida. Okay, so this is about service based companies. Okay, so these are the list of hiring companies you have, like Intel, Qualcomm, Synopsys. Okay, so now Xilinx, AMD acquired Xilinx. Xilinx company is not there. Okay, the AMD is acquired Xilinx, HCL, L&T. Okay, these all are list of hiring companies. Okay, for VLSI engineers. Okay, so basically like VLSI physical design flow, if you see, this is the basic physical design flow. VLSI physical design flow means here basically there is a system specification. Okay, system specification means any client will come with his requirement, like suppose half adder is there, so half adder have how many inputs and how many outputs, like that, system specification. Okay, so we'll do some specification, we'll see the data sheet, and how many modules are required, and what is the type of, what is the functionality of that, so whatever that things will be done in the system specification. Okay. And next, architectural design means we need to do, suppose if you want to design any CPU. Okay. So we need to do some means we need to do some layout in this, and we need to do some connections. Okay. That blueprint we need to do. Okay. And in this CPU, so CPU consists of some memory unit, or ALU. Okay. And bus interface unit. Okay. All these things will do the architecture. So that architecture will be done by this in the architectural design. And functional and logical design means we need to write the program. Okay. By using some HDL languages like Verilog or VHDL. Okay. And so this is logical design and functional design. We need to do simulation. Okay. And we need to verify that circuit. Okay. For verification we need to use ESV and UVM related things we are doing in the functional and logical design and circuit design. Okay. This part is nothing but we call as a front end. Okay. And in the physical design, what they will do, so from the front end they are getting the input from the physical, this front end they are getting the input to physical design. Okay. Some files you are getting, so in the physical design we are doing some partitioning. Okay. Floor planning. Okay. Power planning. So like it's physical design is like it's like whenever you are building, means you are constructing any civil engineer constructing any building. Okay. First what they will do, first they will do some planning, no. Okay. So planning, and after that they will do some means some so foundation they will make, no. And they will make the pillars. Okay. They, and after that they will make the different partitions. Okay. So like that. Okay. So that whenever you want to make any IC, you need to do some partition. Okay. Where the CPU should be in the CPU, where the, suppose if you are designing for SOC. Okay. So where the CPU should be laid, and where the micro memory unit should be laid. Okay. Where this ALU should be laid. That is partitioning. And floor planning and power planning also, how the power is given to each and every module. Okay. Placement. Okay. And clock tree synthesis, routing, and timing closure. So this all will be you are going to read, you're going to study in physical design. Okay. Physical design. And here after this you need to do physical verification and sign off. Okay. After that you need to do fabrication. So in the fabrication you have so many steps like photolithography, and implantation, diffusion, and CMOS fabrication techniques like N-well technique and twin tube technique. Okay. These all techniques are there. And after fabrication there is a packaging and testing and chip finishing. Okay. So this is the basic physical design flow. Okay. So here this is ASIC flow. ASIC flow is nothing but application specific integrated circuit. Okay. So wherever you see you have like ASIC. Okay. So ASIC is nothing but suppose so there are VLSI target devices. There are two types are there in VLSI. There are two things are there. One is ASIC, and next one is FPGA. Okay. So ASIC means wherever you are using, that means ASIC only. Okay. So once program is written, that program will be like that program will be, we can't change the program. Suppose in your home household applications you are using some LED TV or AC. Okay. So like smartwatches which will do the health monitoring. Okay. And in automobiles also we are using for different ASICs for airbags. Okay. Engine control, airbag control. Okay. So that means this is used only for particular application. Okay. Suppose like you are using some mobile, your mobile is supporting 16 GB of RAM and 128 GB of internal memory. Okay. Suppose if you want to upgrade to some 32 GB of RAM and 256 GB of internal memory, so you can't upgrade. That means this is nothing but ASIC. Okay, you can't change, you need to purchase new mobile. Okay, so this is only used for specific application, that is nothing but ASIC. Okay, so in the ASIC, what they will do first, design specification, as I told you, based on the design requirement they will do the design specification, and they will do the architecture. Okay, architectural design. And so architecture, it means what, suppose if you are designing some CPU, so CPU consists of like they will do the architecture of total planning of this CPU, where the ALU should be placed, where the memory should be placed, like that they will do the architecture. And next they will do the micro architecture. Micro architecture means CPU consists of all these modules. Okay, so like this is top down approach, they will do the top down approach. Okay, so they will divide the CPU into sub modules. Okay, like like add ALU, okay, MU, and bus interface unit, and control unit, all these things. Again, these are made with some combinational and sequential circuits. Okay, so that is micro architecture. And RTL design basically they will write the program using HDL languages. Okay, HDL languages are two types, one is Verilog and VHDL. Verilog and VHDL. Okay, so VHDL is nothing but very high speed integrated circuit hardware descriptive language. This VHDL they are using for defense purpose only. Okay, defense and academic purpose only. This is very complex and it will follow some ADA or Pascal type language. Okay, we are not using this, we are using Verilog only. Okay, so basically in the Verilog also we have some modelings are there, switch level modeling, and gate level modeling, data flow modeling, and behavioral modeling. So RTL is nothing but register transfer level. That register transfer level we can use only data flow modeling, and we can use behavioral modeling, and hybrid modeling. Hybrid means a combination of this. Okay, so how the data is transmitting through the register is nothing but we call as RTL design. Okay, so basically you will use this Verilog code for RTL design. We are making the design. Okay, so by using RTL design, so Verilog we are using. And if design is met, it will go to the next step. If design is not met, so if design is met, it will go to the next step. RTL verification. RTL verification means so you need to verify each and every block, each and every corner cases we need to check. So here we need to use SV or UVM. Okay, SV is nothing but SystemVerilog. Okay, so SystemVerilog, some more advanced features are there compared to Verilog. Okay, and here we can use 90% of verification by using SystemVerilog. And UVM is not a language, this is a like a methodology. Okay, universal verification methodology. By using SV, you are writing the test cases for UVM. Okay, so basically like up to FSM we can write the test benches. By using Verilog we can write the test benches, but suppose if you see for complex SOCs or IPs, okay, so you can't write. Okay, so you need to go for SV, SystemVerilog, for verification. Okay, so means what, in SV we are using we are writing test bench only. Okay, so this SV can be used for design purpose also. Suppose 30% we can nowadays they are using that SV for design purpose also. So SV 30% it used for design, and 90% they are using for verification. Okay, so if design is met, it will go to the next step. If design is not met, it will go to the RTL design. Okay, again it will go to that. So these two people will work together. Okay, so RTL designers will design the circuit. After that DV people, ASIC DV people or DV people will verify the circuit whether this specification is meeting or not. They will verify. Okay, so if design is met, it will go to the next step. If design is not met, it will go to the RTL design. Okay, so here they will do the some logic synthesis. Logic synthesis nothing but some constraints are there. Okay, some constraints are there. So nowadays we are using mainly handheld devices, those are battery operated. So we need to take care of these constraints like timing, okay, area, area and power related constraints, okay, that we need to consider, okay. That will be done by the logic synthesis engineers will be there, okay. So synthesis nothing but basically synthesis in RTL, in HDL also we are doing this synthesis. We are converting whatever the program, okay, into gate level netlist. Gate level netlist is nothing but synthesis, okay. So we are converting our design into hardware, that is nothing but synthesis. Whereas software people, they will not create the hardware, just they will develop the application only, okay. But this hardware people, we are the hardware people, we can write the program and we can generate the gate level netlist, okay. And next, DFT, design for testability. So we need to test the circuit by using BIST, built-in self-test, some scan related test. So that will come under the DFT, okay. And next, LEC is nothing but layout, some layout related operations will done in the analog layout will done in this LEC. So STA is nothing but you have some techniques are there that are related to delays, okay. Delays like setup time and hold time, okay, hold time and clock skew, okay. So wherever the delay related operations that will be done in the STA is there in post layout STA and pre-layout STA and post layout STA, okay. Pre-layout STA and post layout STA is there. So if design is met, it will go to the next step. If design is not met, again it will go to the synthesis, okay. So this is PD flow, physical design flow, this I already told, okay. And parasitic extractions means any parasitic means what, any capacitor and inductor inbuilt, if they are there means we need to extract this parasitic extraction. And post layout STA is there, okay. This post layout STA is also there. If design is met, it will go to the next step. If design is not met, it will go to the PD flow, okay. And here also we need to do physical verification. In front end we are doing the RTL verification. In the back end also, after completing the PD, okay, post layout STA, we need to do physical verification, and this is fabrication, okay. So that means GDS2 file will be generated. So GDS2 file will be generated, okay. Graphical display some system GDS is there, so that is given to the fabricators will fabricate based on this GDS2 file, okay. So this is the basic ASIC design flow, okay. Hope you understood this one. Any doubt in this? Yes, is it fine? Okay, this is about the basic ASIC design flow. And next, physical design, we need to do some floor planning, okay. Floor planning means we need to do some planning your floor, okay. So die estimation, okay. So die estimation means you will get a silicon wafer die, okay. Silicon wafer die, okay. In that die you are fabricating all these modules and macro placements, okay. And IO placement, planning of power distribution, that will be done in the floor planning, okay. So what are the goals of floor planning? All macros in placement grid, no macros overlap, okay. So no PG nets or DRC or LVSI violations, okay. Minimize the conjunction and make sure that design timing is meeting, okay. So this is the basic just a snippet of this floor planning, okay. Some RAM is there, RAM design, okay. RAM is so designed here, okay. Like some modules are designing, okay. So based on this we need to do some floor planning. So what are the inputs for PD means one is gate level netlist, okay. So I told you now that synthesis nothing but using HDL languages we are converting this program into gate level netlist. So that is .v file. And constraints, I told you from the synthesis you are getting some constraints, no, power related, area related, and timing related. Those are nothing but HDC file constraints. Some library files you are getting from the library files, okay, and physical library files, okay, LEF files, and voltage domain designs, okay, UPF files. These are the input for the physical design. Okay, so this is floor planning full chip. Okay, so this is floor planning full chip with different corner cells, IO cells. Okay, like this different floor planning full chip is there. And IO planning means we need to do some. We receive different types of input from FE regarding IO pins. Okay, address bus, data bus. Okay, so we need to plan this IO planning. Okay, and next these are the floor planning elements, where is the core area and die area. Okay, standard cells means so like in ASIC we can do this by using two methods. One is full custom and semi custom. Full custom means semi custom. Okay, full custom means we need to come from the scratch. Okay, so we need to come from the scratch. Semi custom means we can use some standard cells. We can use from standard cells. Suppose standard cells are predefined cells, so those are already available, like AND gate or flip flop or adders. Okay, or some counters. Those are already predefined available ICs are there, so that we can replace based on that dimensions. We can replace. Okay, so that is the standard cells. And this is placement. Okay, so what are the goals for the placement? Less utilization jump, no congestion, no overlap, good timing values. Okay, so this is about the placement. And clock tree synthesis means here there is a global clock. So each and every module will not take same clock, no. So that means you need to divide. Inside there will be a clock divider circuit that divide the clock. So how much of clock is required for the module, that much of clock we can distribute. Okay, that is nothing but clock tree. By using this clock tree synthesis only, we can divide this clock into different modules. Okay, and routing is nothing but basically connections we need to do. Okay, this is like we need to do some connections in this. Okay, that is routing. Okay, and sign-offs means we need to check for electrical, we need to verify. Okay, physical verification and crosstalk or noise. Okay, so these we need to do in the sign-off checks and physical verification. Okay, so this is about the basic physical design. Okay, physical design. And coming to the design and verification in VLSI, so everywhere you see there is a VLSI is there. Suppose microprocessors, that is in personal computers, laptops, you have microprocessor is there. Okay, and graphic card is there, digital camera, camcorders, cell phones. Okay, cell phones, embedded processors, everywhere you see you have VLSI is there. Everywhere VLSI is there. Okay, personal entertainment, medical electronic system, everywhere you have VLSI is there. Okay, so what are the main devices we are using in VLSI? Microprocessor, system on chip, and FPGA. Okay, these are the main devices. Okay, so microcontroller is nothing but we are using only for specific application, that is nothing but microcontroller. So inbuilt, there will be inbuilt CPU, ROM, serial interface, RAM, timer, IO ports within an IC. Suppose 8051, this is a basic microcontroller. Okay, so microcontroller, it is a 40 pin IC. So inbuilt there is some different so it have 4 kilobytes of RAM and 128 bytes of ROM. Okay, like that it will be there. Okay, so this is only used for specific application. Okay, that is nothing but microcontroller. So the clock speed is around 1 megahertz to 300 megahertz. And microprocessor is nothing but basically we are using for general purpose. So in our laptop or desktop you have microprocessor. It consists of some ALU, register array, or control unit. Okay, so ALU perform whatever the arithmetic and logical operations are there. So I think you already studied about this 8086 microprocessor. Okay, so 8086 microprocessor, that is same thing. So clock rate is 1 gigahertz to 4 gigahertz. Okay, and next is system on chip. System on chip means it consists of ARM processor and some different peripherals are there. Okay, like Ethernet, USART, universal synchronous asynchronous receiver, serial peripheral interface, two-wire interface, ADC, okay, analog and digital converter, CAN, okay, control area network, USB, and PWM, okay, pulse width modulator, synchronous serial timer counter, okay. So all are connected with a AMBA. This is nothing but AHB or ASB bus, okay, APB bus, okay. So all SRAM, flash, all in a single IC, okay, we call as system on chip. Suppose your processor in your mobile is there now, okay, which processor you are using, Qualcomm, Snapdragon, okay, some process you are using in the mobile, that is nothing but we call as SoC, okay. Raspberry Pi also, okay, Raspberry Pi which we are using for embedded projects, okay, those are nothing but is system on chip, okay, SoC. It consists of inbuilt processor and some LAN inbuilt LAN drivers are there, LAN ICs are there, memory is there, okay, all are connected with this AMBA protocols, okay. So AHB and APB bus, okay, this is system on chip. FPGA is nothing but field programmable gate array. It consists of some CLBs, configurable logic blocks. Okay, so configurable logic blocks, and these are IO blocks. Okay, so we can configure or we can reprogram this FPGA. Okay, so basically FPGA consists of SRAM. Okay, SRAM means what? So when power is shut down, all the programs will be erased. Okay, so here we can use this FPGA for R&D purpose. Okay, R&D purpose we can use this FPGA. Okay, so suppose if you want to design any FSM, okay, or sequence detector, okay, sequence detector, you can write the program in Verilog, and you can port that Verilog program, you can generate the bit file and you can port into that FPGA, so that FPGA is acting as a FSM. Okay, so for R&D purpose we can use, okay, and here we can use this FPGA in defense also. Okay, if we can use in defense, or we are using in cell towers. Okay, cell towers why you are using means previously in the cell towers we use 3G or 4G, okay, 3G or 4G, okay, so now we upgraded toward 5G. Okay, suppose in future we will upgrade toward 6G. Okay, every time what happens, this is a cell tower, so every time we can't remove this whatever the equipment from the cell tower, no. So what they will do, so based on the requirement, now previously suppose like 3 years or 4 years back there is a 4G, so 4G program they will load in this FPGA. Okay, FPGA, after that what happens, so means now 5G came, so 5G came means here now 5G will be loaded into the FPGA. Future if 6G is coming means, so 6G we can reprogram. Okay, so that means inside backside means in the ground station there will be always generator is there, generator. If power is shut down, what happens, through this generator this will be operated. Okay, I told you now in FPGA whatever the program when it is shut down, so it will be erased. Okay, that's why every time the power will be supplied to this FPGA. Okay, so this is one operation. Okay, in defense also, suppose if they want to do some advanced techniques, okay, they want to upgrade their systems. Okay, so like if they are using ASIC, they can't, those are costly. Okay, the whatever the defense equipments are, those are costly. Okay, they can't purchase again and again. Okay, so what they will do, they will upgrade, they are using FPGA in their defense system, and they can upgrade with the software. Okay, so this is about FPGA. Okay, this design flow already told. So I told you, know, ASIC and FPGA. So FPGA is nothing but we can reprogram. ASIC is nothing but so here see here, reprogramming with collection of hundreds of thousands of logic gates. We can reprogram in the ASIC, okay, in the FPGA, but in ASIC this is only used for specific application. Okay, specific application. I will tell you with one example. Suppose like suppose olden days you use some ACs. Okay, olden days, suppose 5 years back you are using this ACs. Okay, you are using ACs. Nowadays you got ACs with the technology, latest technology, IoT and AI. Okay, so with your mobile you can operate your AC. Okay, with some AI features also coming. Okay, that means it consists of some AI processors are there. Okay, and performance is also good. So can you upgrade this 5 years old AC with this AC? You can't upgrade. Why? Because this is ASIC. Okay, we can't change. Okay, once it is programmed we can't change. Okay, so we can't upgrade. So that means like this, these are nothing but this is only used for specific application. Suppose like mobiles also, suppose you are using some 3G, some person, he is in village, he are using 3G mobile. Okay, 3G mobile. Now all the whoever the customer, they upgraded to 5G. Okay, what this network provider will do, this will convert this 5G 3G into 5G. Okay, so automatically this 3G will be, network will be down. Okay, he'll come to shop and he will ask, okay, my network is not coming, like that means how what the shop person will tell. So now we all networks we upgraded to 5G. Now that's why the 3G is down. So one option is you need to purchase new mobile. You should purchase new mobile which will support 5G. Okay, okay, otherwise no option, you can't upgrade this 3G mobile. Okay, you can't upgrade. Why? Because this is what ASIC, this is what ASIC is. This is used only for specific application. So he can purchase so that he will get the 5G network, like that. Okay, so that means we can't upgrade. Once it is purchased or once it is programmed, we can't change. That is nothing but ASIC. Okay, so mainly these are the two target devices for the ASIC. Two target devices for the ASIC. Okay, so this is FPGA flow. So basically like we are using Xilinx Vivado, that is AMD. Okay, I told you, know, first you need to write the Verilog code. Okay, Verilog code. After that we are doing synthesis. Synthesis is nothing but we are converting our program into gate level netlist. Gate level netlist. Okay, after gate level netlist, what you are doing, you are implementing. Okay, so in implement you need to translate, map, place and route. Okay, after this translate, map, place and route, it will generate the bit stream. Okay, this bit stream we need to port in the FPGA. Okay, so port into the FPGA. Okay, so Vivado tool, whatever the Vivado tool is there, that will convert HDL code into the schematic netlist. You'll get the schematic netlist that I will show in the Vivado tool. Implementation will be done based on the target FPGA. So what is the implementation? We need to do floor planning, routing, placement, mapping. Okay, then that whole will be done in the implementation. After implementation, bit file will be generated, that we can port into the FPGA, so that that FPGA will be work as a our suppose if we want to design a counter, we can write the Verilog program, we can generate the bit field and we can port into that FPGA. FPGA is acting as a counter, right? It may be synchronous or asynchronous counter. Okay, so design closure means we need to do functional closure. Okay, so through means we validate the functionality of the circuit. Okay, that is functional closure. Power related it should take low power. And timing closure means we need to do some static timing analysis. Okay, clock domain crossing and reset domain crossing. Okay, so that means clock domain crossing means we are not getting same clock for all the circuits. Okay, we are getting different clocks for different modules. Okay, and that is nothing but whenever we are studying about this different clocks, that is nothing but clock domain crossing. And reset domain crossing, reset related related thing we need to study in this reset domain crossing, that is nothing but timing closure. Okay, so basically like course overview, if it is front end RTL design, we will teach digital electronics, we'll teach Verilog only. Okay, this VHDL we are not teaching, and we'll provide two Verilog projects. Okay, and we'll teach static timing analysis, CDC and RDC. Okay, linting also will teach. Okay, this will come to the RTL design. If it is DV, okay, ASIC digital design verification course, uh, digital electronics and Verilog will teach. After that, we'll teach System Verilog assertions will teach, and UVM will teach. Okay, and some projects also will. This is nothing but SOC verification. Okay, so by using this System Verilog, we'll give some projects also. Okay, so this is course overview. And basically I told you, like Verilog and VHDL. So Verilog is a high level language, easy syntax, so it will follow C syntax. If you are comfortable with C, you can learn Verilog easily. Okay, easy to learn. And multi-level abstractions are there. Multi-level abstraction means modeling styles are there, like switch level modeling, and next you have gate level modeling, and next data flow modeling, behavioral modeling. Switch level modeling means with the help of these transistors you need to model, that is CMOS. Gate level means in terms of gates. Okay, these are non-synthesizable. Data flow means in terms of expression. Suppose sum equal to A XOR B, you need to represent a continuous assignment statement. Behavioral modeling means you need to use if else or case statement. Okay, the procedural statements we need to use. Okay, so basically we are using RTL coding by using these two modelings, data flow and behavioral modeling. Okay, and VHDL, this is hard syntax is there, controlled language. Basically this came into picture around 1999, means into market, came into existence. This IEEE will be there, no, Institute of Electrical and Electronics Engineers. So they will make this as a universal language. Okay, so around 1999 it came into picture, and 2001 it came into picture. Okay, so this is universal wherever you will go. This is universal. Okay, corporate in RTL design they will use Verilog only. Okay, so this they are using in defense or academics. They are using this VHDL. Okay, hard to learn. Okay, so this will follow the old language, like old language is there, ADA or Pascal. Okay, Pascal, and multi-level abstraction is there. Okay, suppose if I write a simple program using what for AND gate. For AND gate, if you see simple program, let us take the inputs are what, A and B, and output is Y. Okay, so if I am using Verilog program will start with module and end module. Okay, module, and this is nothing but we can call as a module name, or we can call as identifier. Okay, and underscore gate identifier, and input A comma B, output Y. I am using a continuous assignment statement. Okay, this is continuous. Okay, continuous assignment statement. Okay, we can call as this is data flow modeling or structural modeling. Okay, assign Y equal to A and B. This is bit level operator, bit level AND operator, end module. Okay, so 3 lines of code are there. Okay, if it is VHDL, it will take so much of code. See here, library IEEE. So I need to initialize the header file, library file, use IEEE.std underscore logic underscore 1164 entity. In the entity I need to declare the input and output, A in std IO logic, in std logic, out std logic. Okay, in the architecture I need to write the logic. Okay, architecture of AND gate is begin Y equal to Y and B. So it will take around 10 lines of code. Okay, so it will be complex. Okay, it will be complex, but it is easy to learn. Okay, so this is about Verilog. So this is analog layout. You are going to study about floor planning, placement, matching, and basic design rule checks, routing, layouts versus schematic, DRC, post layout, silicon, and tape out. That we will study in the analog layout. Okay, floor planning, placement, Basically you will design with stick diagrams only, so that CMOS circuits are there. CMOS circuit you design the layouts. Okay, this is schematic. Okay, this is schematic, my CMOS schematic, and this is nothing but layout in terms of stick diagrams. Okay, stick diagram. Okay, so that you will study in the analog layout. Okay, this is placement matching. Okay, base DRC. Okay, routing means some connection, how it will be connected. Okay, design rule checks, common DRC errors. Okay, so like this you will study in the analog layout. Okay, and AMS is nothing but analog and mixed signal and custom IC layout. Okay, so both AMS means so we'll study about both analog as well as digital. Analog as well as digital you will study. Okay, so this is about fully developed analog RF layout. So ASIC chip design flow I told you. Okay, that same thing like architecture, RTL design. Okay, RTL design, specification, architectural design, RTL verification. Here you are using Verilog, here you are using what SV and UVM. Okay, and here synthesis, gate level simulation, design for test, DFT. So this is a total physical design, floor planning, placement, clock tree synthesis, routing, and this total comes under the PD. Okay, and here specification to gate level simulation. This is front end. Okay, front end, VLSI front end. Okay, VLSI front end you will get. Okay, from here to from DFT you will get back end. Okay, back end you will get. Okay, floor planning. Okay, back end, sign off of fabrication, post silicon validation, and chip. Okay, so this is ASIC or chip design flow. So about Gnanodaya, if you see, this is a premier institute in advanced VLSI studies. So located in both Bangalore as well as Hyderabad. So in Bangalore it is located in Martali. Okay, in Hyderabad it is located in SR Nagar, just walkable distance from SR Nagar metro station. Okay, metro station. So whoever the faculty trainers are there, those are 15 plus years of experience are there, proven track record on the placement. So previously two students got placed in in some two companies. Though those are analog layout students. Okay, and unique feature of Gnanodaya, 100% placement assistance will be given, and the curriculum is industry standard course curriculum, and VPN based 24/7 lab support will be given. Okay, a low cost and a low value for money. Okay, so VLSI is everywhere. If you go healthcare, telecommunication, okay, or automobiles, consumer electronics, VLSI is really everywhere. So basically we are using ASICs only. Okay, ASICs only, VLSI we are using ASICs. If you go for defense or like if you go for some communication related, they are using FPGA. They are using FPGA. Okay, carrier guidance and placement cell, 100% placement assistance will be given. Okay, so any placement requirement is coming, first we will take the requirement from the client. Okay, we will assist the student for preparation for resume as per the requirement, and we'll send the student resume to the client. Okay, so based on the requirement, the client will shortlist the candidates to attend the written test and interview. Okay, after completing written test and interview, they will announce the final selection. Okay, so at least you need to clear 2 rounds, either written test or interview. Remaining part will take care. Why? Because we have some connections with the HRs. Okay, so that we can take care. Okay, but at least you need to clear the 2 rounds of interview. Okay, and next, gateway for semiconductor industry, Gnanodaya VLSI. Okay, so this, and eligibility criteria should be BTech, BE or BTech. Basically you need to study either EC or EEE. Why? Because first basic subjects will come, like digital and analog. Okay, digital electronics, analog electronics, and you will study about RTL. Okay, you study about Linux, Linux, Tickle, okay, and STA, static timing analysis, and Fab also. Fab. These are some basic related things. Okay, so these are there for EC and triple E students. If civil and mechanical means, then these are not that much. Uh, 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 that much means it will be there in the first year, but digital is not there. Okay, it's difficult to understand. Okay, that's why the eligibility is they should be either EC or triple E. This is the basic for the entering into VLSI. Okay, they should be ME or MTech VLSI or electronics related, and minimum 60% in graduation. Good communication skills are required. Okay, so training process is first is registration, discussion fee, and course. Okay, training period will be 6 months. Okay, preparation with the mentor support, conducting mock interviews, 100% placement assistance will be given. Okay, so basically like three are there. Physical design, this is 6 months, daily 1 hour class will be there. So weekend batch, if it is weekend batch, 6 hours per week will be there. So number of students intake is 15 to 20 only. VPN support will be there, and 15 plus years of experience, and 100% placement support will be given. Okay, unlock layout also same thing, just the duration is 4 months. Okay, and ASIC verification also the duration will be 4 months. Okay, and ASIC RTL design course is also there. RTL design, ASIC RTL design means will teach this digital Verilog, and this CDC linting, RDC. Okay, all those things we will make you to train this in this ASIC RTL design. Verification means we'll teach along with digital and Verilog, will teach SV and UVM. Okay, UVM and some assertions will teach. Okay, so now fees is 85,000. Okay, if it is MOE means it will be 80,000 only. This is not yet updated. 85,000 fees. So this is these are the contact numbers you can contact. Okay, contact number, email, and this is our website. Okay, so any information, any related queries, you can contact. So we have the pages in the YouTube pages, in Instagram pages also there. You can follow those. Okay, so this is about so hope you noted this contact numbers and email. Okay, so just I want to show you the just I want to show you yes, uh, I want to show you about so one program in Xilinx Vivado. Okay, so and also Quastasim also I will tell you. So basic all gates are there. Suppose I am opening this. Verilog programs. Verilog programs. All gates using GLM. This is all gates using GLM. Okay, gate level modeling. All gates using gate level modeling. So all gates are nothing but what we designed by using all gates, AND gate, OR gate, NOT gate, XOR gate, XNOR gate. Okay, and buffer. Okay, buffer, inverter, all those things I will write. I wrote in GLM, and I will show you how to execute this by using Xilinx Vivado. Just you see, so this is the sources. So here all gates. Okay, all gates. Okay, so here you see I wrote the program using what gate level modeling. Okay, this is by using gate level modeling. Okay, so Verilog will start with what module and identifier all gates underscore GLM. I'm using a vectors input 1:0 in. Okay, so for in I'm giving two inputs, in 1 down to 0. Okay, so outputs I'm initializing output y and y or y NAND, y NOR, y XOR, y XNOR, y NOT, y buffer. Okay. So gate level modeling will be like this. That means gate level primitive. This is predefined word. And, or, NAND, NOR, XOR, XNOR, NOT, buff. These are predefined. And the syntax will be like this: output followed by input. Okay. Y and in 0 in 1. Okay. Or Y or in 0 in 1. Okay. NAND, Y NAND in 0 in 1. These are the inputs. In 0 in 1 are nothing but inputs, and this is nothing but output. Okay. XNOR, Y XNOR in 0 in 1, not Y not in 0 in 1, Y buff in 0 in 0. Okay, only one input will be there, no? So this is the program. And if you see the test bench, so this is the test bench. For verification purpose, you need to write the test bench. Okay, one second. For verification purpose, you need to write the test bench. So module all gates underscore GLM TB, reg 1 is to 0 in underscore TB. Okay, this is the input for the test bench. We are giving the stimulus to the design through the test bench. Okay, so reg 1 is to 0 in underscore TB. This is, you need to use reg data type, and whatever the outputs are there, you need to use var data type, and I need to instantiate the design. Okay, so this I am using instantiation by position, means how you declared that inputs in the design, that same thing you need to declare here. There are two types of instantiation are there: instantiation by position and instantiation by name. Okay, that name also I will tell you. I am initializing integer I, initial begin, dollar monitor means if there any change in the inputs, okay, it will display the outputs. Okay, and I am using for loop. Okay, so for gates you have two inputs. How many possible combinations I need to check? Four possible combinations I need to check: 0 0 0 1 1 0 1 1. Okay, and for I equal to 0, I less than 4, I equal to I plus 1. Loop statement begin in of TB equal to I, and I am executing for how many time units, means 20 time units I am executing. And if you want to finish, if you want to end the simulation, you need to use dollar finish. Okay, so here what I am doing, one second. So here if you want to see the waveform, so means if you want to see the circuit, open, okay, save this, open the elaborated design, open the elaborated design. Okay, so reading the netlist, it will create the elaborated design. Okay, just wait, it will create. See here, this is elaborated design. Okay, so elaborated design, if you see, so how many inputs are there? Two inputs are there. It is coming through the buffer. Okay, and this is AND gate. AND gate means what? Y and NAND gate, Y NAND. Okay, AND gate followed by this inverter is NAND gate, and here you are getting, this is nothing but NOT gate, and this is a buffer. Okay, coming directly through the buffer, and this is OR gate, YOR, and OR gate followed by an inverter, NOR gate, XOR gate, this is Y XOR, and next this one is XNOR. So XOR gate followed by an inverter is nothing but XNOR. Okay, so here if you see, I want to simulate this, run behavioral simulation, run behavioral simulation. Okay, I want to see the simulation behavior of this all gates. Okay, just I am simulating. So see here, so here you got the waveforms. Okay, in TCL console also you will get the output. See here, TCL console, see here, in is 0 0. These are the outputs of all the gates, and underscore TB 0. Okay, R underscore TB 0. Okay, in TCL console you can see the for four possible combinations you will get. Why? Because in the test bench you wrote dollar monitor, no? So dollar monitor means it is displaying this in the TCL console. Okay, and in the waveforms also you can see. Okay, just expand, fit to page, and here two inputs are there, two inputs. See here, so here when inputs are 0 0, What is the AND gate output? 0, and OR gate output is 0. NAND gate output is what? 1. NOR gate is output is also 1. Okay, like that. Okay, you will get. Okay, and next, if it is 0 1, 0 1, okay, AND gate output is 0 and OR gate output is 1. Okay, like this. And this is for 1 0, and this is for 1 1. 3 means what? 1 1. Okay, 1 1. 1 1 means AND gate output, both AND and OR are 1 1, and XOR is 1. XNOR is 1, and XOR means what? OR detector. Both inputs are same. The output is 0. NOT gate 0. Buffer gate is 0. Okay, like this you can see. Okay, and if you see the DFM, data flow modeling, the only change is what? This is DFM. Okay, DFM, just I will open. Test bench is same only. Okay, test bench is same only, but there will be difference comes in the one second, I'll close this. Yeah, I'm opening the DFM. This is DFM, data flow modeling, all gates data flow modeling. So in the data flow modeling, what you need to use? You need to use the continuous assignment statement. Okay, you need to use continuous assignment statement. So see here, it's opening. Test bench is same only. Test bench I am not telling. The test bench will be same only. Okay, so here if you see this this one, so if you see this program, module all gates underscore DFM. So input I am initializing 1:0 in. Output is what? Y and Y or Y NAND, Y NOR, Y XOR, all these things. I need to use what? Continuous assignment statement. Okay, and I need to initialize with this expression. Okay, so Y equal to Y to Y, A and B. No, I need to use a logical bitwise, not logical, bitwise logical, bitwise AND operator, bitwise OR operator. Okay, this is NAND. Okay, AND followed by negation is nothing but bitwise NAND, OR followed by negation, bitwise NOR. This is XOR. Okay, and XOR followed by negation, XNOR. Okay, XNOR, this is XNOR, and NOT and in 0. Okay, so this also I can see. Okay, so means here you will get elaborate design, you will get the same thing only. Okay, behavior modeling also you can write. Okay, you can execute for all gates. You see, just I am elaborating the design. Yeah, same waveform I see here. Same waveform, same I elaborated the design. No, same design I got. Okay, whatever the design I explained, same design I got. Simulation also same I will get. Okay, just I am changing the modeling. In first what I did, I wrote the modeling by using I use the style, modeling style is gate level modeling, and this one is nothing but data flow modeling. I am using the styles. Okay, different styles. Yeah, so this is simulation. You see, this is the simulation. Okay, fit to page, I got the different values of the in 0. Okay, in 0 is 0 0. So what are the outputs? And in 0 is 1 1 and 1 1 2. What are the outputs I will get? Okay, so this is about Xilinx Vivado. So in QuastaSim also you can write. So in QuastaSim what you need to do? So you need to create some folders, and I need to use GVim editor. Okay, so one second, I'm open this in QuastaSim RTL codes. Okay, I wrote for all gates. Okay, so if you are using QuastaSim, what you need to do? You need to create 3 files, that is RTL, simulation and TB, and this is a work function. Actually in sim only work function will be created. So here I created, this is not required. Okay, so this is not required. In simulation only work function will be created. Okay, so here what I am doing in RTL, I wrote all gates GL, I'll get GLM. Okay, this is GVim. GVim is a powerful editor. Some commands we are using. So basically in the industry they are using GVim only. Okay, so GVim, same code I wrote. Okay, same code I wrote, and in the test bench also I need to write a separate program for GLM. Okay, so this is the separate program for GLM. Okay, so if I want to execute this, I need to open this QuastaSim. Okay, model sim also you can write. So model sim you can write only Verilog codes. You can execute this Verilog codes, but in QuastaSim you can execute both Verilog and SystemVerilog and UVM related. Okay, so this is a transcript window. In the transcript window only I am executing this programs. Okay, so here what I am doing here, this is simulation is there, no simulation, this path. Okay, in file folder simulation path is there, no, so just I am copying. So what I am doing, cd space colon, I am copying this path. Okay, so I am copying this path, flower bracket close. Okay, so ls. Okay, ls means it will be in that these files are there. Okay, list of the files, these files are there, and I need to create. So first I need to remove the work function, vdel minus all, one second. Okay, I will create one work function, vlib work. Okay, vlib work. Okay, already exists, it's coming. vmap work. Okay, after that vlog dot slash, I need to go to RTL, and I need to execute DFM I will execute. Okay, plus ACC I need to keep. Okay, plus ACC. Okay, so this is for compilation, means I need to check any errors are there in my program or not. Okay, and next vlog dot slash tb slash, here DFM, where is DFM? This is DFM. Okay, this is TP file, no need to give plus ACC. So 0 error 0 1. Okay, so this is my TB1. Okay, this is my file, vsim. Okay, copy this. Okay, enter. Okay, simulation will start. Okay, simulation will start. So this is only for simulation only, we can't see the circuit. So go to dout. Okay, dout, and add waves. Okay, the waves will be added here. Okay, waves will be added here. You need to keep run minus all. Okay, run minus all, no. Okay, no, and expand this, just fit to page, where you got this one. Okay, this one, fit to page. Okay, so I got the waveform, see here. So this is these are the inputs. Okay, these are the inputs in 0 means two inputs are there, no, so in 0, in 1. Okay, so when it is 0 0, what are the inputs, y and y nor and y or okay, when in 1 0 0 1 1 0, like this you can see the simulation in the QuastaSim. Okay, QuastaSim you can see. Suppose I don't want all these programs. Suppose if you want to come out of the simulation, quit sim, it will come out of the loop. Okay, so here see here, so here during the test bench, so all the possible combinations and our output also it displayed in the transcript window. Okay, transcript window. Suppose like I don't want to execute all these commands. Okay, so what I need to do in the work function, I need to create what in the work function, in the sim, I need to create a run file. Okay, this is my run file. Okay, so from vlib work to run all, I need to copy this, and I need to create this run dot do. Okay, so directly in the QuastaSim, what I am doing, do space run dot do. Okay, do space run dot do. Directly the simulation will be opened. For every file we need to create the do file. Okay, so here no, Okay, so directly you will get the output. See here, fit to page. Where is fit to page? One second. Logic page. Okay. This is fit to page. See here, you got these waveforms. Okay, so for different values of inputs you got these waveforms. Okay, directly if you press this dot space run dot do without using that command, so you will get that waveforms. Okay, so this is about QuastaSim. Okay, so we can run the Verilog codes by using Xilinx Vivado, or we can run the programs by using QuastaSim. Xilinx Vivado, we can elaborate the design. Okay, so just I'm closing. We can see the how the design will look like. Okay, we can see this elaborated design. That elaborated design we can't see in QuastaSim. Okay, we can see only simulation only. Okay, so the use of QuastaSim means if you are using model sim means we can write the Verilog codes only. But if you are using QuastaSim, if you are going further, if you want to write for SV related test benches and UVM related test benches, so there you can use QuastaSim also. Okay, so this is about today's session. Second.